Hi, good morning and welcome to another lecture of information security. Today is our second real part of cryptography, and today our plan is to talk about encryption. So, in case you've lost track a bit of what we were last talking about, previous week we were talking about symmetric schemes to protect the integrity of data. So specifically we had a look at hash functions. We didn't quite have time for the max, but I'll talk about them briefly in a moment. Today we're going to talk about a different big security goal that we want to protect or that we want to achieve, and that is confidentiality. And here we're going to look at actually two layers of the solution to this problem. The first layer is the top layer, what we actually want to have. That's a so-called encryption scheme. Or specifically today, if we have time, we also look at authenticated encryption, which is encryption as it should be. And we are also going to have a look under the hood, so on the layer below, because last week we've already seen that hash functions use these magic primitives, and today we are going to have a closer look at one such primitive. The following weeks we are going to look a bit further up the stack again, so next week we are going to talk about asymmetric cryptography, and the week after we're going to take a sort of bird's eye view to see how all of these building blocks fit together in protocols to actually protect our data. So let's have a brief recap of last week. We talked about schemes for message authentication, actually just one type of scheme. So what all such authentication schemes have in common is that they take a message input and produce a fixed length tag from them. So the tag is a short piece of data that is a sort of checksum or fingerprint of the message. So if the message changes, the tag will change. And if the tag is unchanged, conversely, we know that the message is still correct. It was not manipulated. And in some cases, we also have some keys involved. So last week, we were mainly focusing on this first case here, so-called keyless or unkeyed authentication, which go by the more handy name of hash functions. So here I have a summary overview of who actually can do what. In case of hash functions, there was no key or anything. That means that anyone knows the specification of the hash function and can compute the tag, but also everyone can verify it. This is great because it makes it very flexible for many situations, but there are situations where I don't actually want everyone to be able to compute the tag, because that means that somebody who manipulates the data could also override the tag with a newly computed tag of the corrupted data, because they can compute it. And to solve this issue, we have MACs. So here we have a so-called symmetric key. Both parties have the same key. We'll get to that in a moment and talk mostly about this setup today, actually. And here, only the people who have the key can either compute the tag or verify it. So they're a small team of insiders, and it's protecting against everybody else. There is a third type which we'll only get to next week, and those are so-called signature schemes, which provide authentication in an asymmetric setup. What do we mean by asymmetric? We mean that the communication partners don't all have the same capabilities. So here they have the same, here they have the same, but here it's different. Only the owner of the key can compute the tag, but everyone can verify it. So it's not just a small team of insiders talking to each other, excluding everybody else, but here everybody can actually verify. So now let's have a recap of how these things were built, in particular the hash functions that we saw. We saw that to achieve this for arbitrarily length data, we still need one fixed size building block that we can work with, that we can implement. And this is the so-called compression function, which takes a fixed size input and produces a smaller but also fixed size output. Smaller because the input is T plus M bits and the output is just T bits. And we can use this scheme in the so-called Merkle-Darmstadt construction to build a hash function which works for input of arbitrary length. Here we can just work with M-bit blocks, but if we iterate this, take the first block, update an intermediate hash, take the next block, update an intermediate hash, and so on, we can actually process messages that are arbitrarily long. And the final intermediate hash is at the same time the final hash. We have a visitor, I see, so can say hello to Her Majesty. So after this recap of stuff we did have time for, here I just want to add a few things that we didn't have time for last week, which includes you, right? We didn't have time for you last week. So, and this missing piece is message authentication codes. So the middle version on the picture I showed before, where both parties have a secret key. So this means that the picture of a message authentication code actually looks very similar to the picture of a hash function. The only difference is that we don't input only the message, but also the symmetric key. And the tag will depend both on the message and the key. So we can also say this in mathematics. A message authentication code is a keyed hash function, HK. So we always denote the name of the function with H, and this subscript K means the key that it takes. And it maps a K-bit key and a message of arbitrary length to a T-bit tag. And this tag again protects the integrity and authenticity of M. There is one big difference to hash functions. In hash functions we said that the challenge of protecting M is shifted to the challenge of protecting T. But in MAX it's different. We don't actually have to protect the tag anymore. What we need to protect now is the key. So we have a new asset that's different from the case of hash functions. And this allows us to use the message authentication codes a bit differently. If you remember, in hash functions we said that if somebody wants to send a message, they hash it. They can send the message on an insecure channel where Eve can manipulate it, but the tag has to be protected somehow. We had this extra protected channel for that. In MAX we don't need to do that because we don't actually need to protect the tag. Instead, we just need to hold on to our key. And not just hold on to it, but before we start working with it in the first time, we need to share it with our communication partner. Otherwise, they won't be able to verify the tag. Because to do this, they need to recompute the MAC and compare whether the tag they get from this computation matches the one that they received over the channel. And if Eve now tries to manipulate both of them, since she doesn't have the key, she doesn't know how she would need to change the tag in order to fit a manipulated message. So that's the big difference to hash functions. And that makes them useful in many situations where hash functions are not sufficient. So what is the security notion for this? If you remember, what did we say as a security notion for hash functions? We said that they need to be collision resistant, pre-match resistant, and second pre-match resistant. And for MAX, we have a different notion, which takes the key into account. Namely, the security notion for MAX is the following. It's called unforgeability. Whoops. And it says it must be infeasible. So an attacker can't possibly achieve it. So it's infeasible for an attacker to produce any new valid message tag pair, even if they can query tags for any other messages of their choice. So what does that mean exactly? If we go back to the previous picture, it means that Eve is allowed to see many pairs of messages and corresponding tags, and she can even trigger Alice to authenticate and send along any messages that the adversary chooses. So she's really powerful, has a lot of influence over Alice. But Eve can still not create any new such combinations of her own, even if she has seen many combinations that are valid before. If she tries it with a new message, she doesn't know how to find the corresponding tag. So what are some generic attacks for this? In the MAC case, in the hash case, we saw that the main generic attack is that you try to brute force a message that gives the right tag, or you try to brute force two messages to find a collision. So the output size of the hash function was the critical parameter. This output size is also relevant here, so it's called T. And of course, if you have a particular message which you want to forge for, so forge is fälschen in German, then you can simply try all 2 to the T possible values of the tag, and one of them will certainly be correct. So you will need many tries, and you cannot even verify by yourself when you found the right one. This is why we call these tries online tries. So if Eve wants to forge something, she can try out all possible tags and send each combination of the forged message and this attempt tag to Bob. And Bob will, well, tell her in 2 to the T, -1 cases, no, that's wrong. And in 1 case, Bob will tell her, oh, that's actually a valid tag. So of course, it's very suspicious, and it usually cannot be done in an undetected way. Because Bob will notice at some point that something is wrong. So here we have, for the first time, the situation that we cannot just computationally attack something, but we have an additional metric, the data. And of course, I can also do some things locally, offline, without asking Bob for help. And this something is to try out the different keys that I have available. So for example, I can simply exhaust all keys and have a look at whether they would hash my particular also some old messages that I know to the old tags that I know. And if yes, it's probably the right key. Okay, so this much for security notions. What are MACs now actually used for or good for? Now, the list is very short here, but it's actually very powerful. So in particular, the second point here. Let's first look at the first point. This is an example we've seen in the first lecture already. MACs are used as a building block in some entity authentication protocols. So in challenge response protocols, like for example in mobile TAN systems, there you find these MACs to compute the little numbers that you then either have to compare between the computer and the phone or type from the computer into the phone. And the other very, very big application area for MACs is, well, in any sort of communication protocol really, in order to protect the integrity of all the data that's transmitted. So you will find MACs, for example, in the HTTPS protocols, or when you SSH connect to a server or other machine, and so on. So all of these authentication protocols really use MACs. Since we have a nice and empty slide now, I can have a look at the question that we already got here, apparently. Okay, it's not really on topic, but I can answer it anyways. So the question, which currently doesn't show up for some reason, is whether my slides are done in LaTeX. Yes, they are. So slides in LaTeX can be created with LaTeX Beamer. That's a package for slides. Okay, let's get back to the presentation. And let's get back to the recap quiz actually. Because now that I've added the stuff we didn't have time for last time, we can go for the quiz, which again has a few questions that you should be able to answer either if you've paid attention in the last 10 minutes or last week. So let's give it a little time, and for the other ones who are already in, to not be bored, let's have a look at the cat. So that's great timing of you, Hexe. Let's see, we currently have 60 people in there, so let's wait for a moment longer, but not too much. Okay, that looks good, so I guess we can start. Whoops, the quiz disappeared. Oh, I love it when Menti is unstable. So, which security goal is closely related to authenticity? Is it A, confidentiality, or B, integrity, or C, availability, or D, non-repudiation? Okay, it appears there was a tie between two answers, so one of them is the correct one, and that's integrity. So integrity means checking that the message wasn't modified in transit. And that's of course a necessary prerequisite for achieving authenticity, so being sure that the message is from who we think it is. So for this reason, I would call it closely related. I do understand a bit why some of you tick the other answer, that's I think confidentiality. And that's because if we want to achieve confidentiality, we usually also value the data enough that we want authenticity from it. So in a sense, it's also related, but not as closely as integrity, because you really cannot have authenticity without integrity. Okay, let's have a look at the next one. So this one says, what is not a useful authentication factor? A, something you know, B, something you are, C, something you sell, or D, something you have. Okay, here the great majority is on the right answer, namely something you sell doesn't make sense as an authentication factor. All the other three were authentication factors that we discussed last time for entity authentication protocols. So something you know would be something like a password, something you are is something biometric, and something you have is, for example, a key or a key stored on a device. So this is an object that stores your secret, essentially. Then next one. For which of these do you need the secret key to verify the authenticity? A for MACs, B for signatures, C for hash functions, or D for password hashing? Yes, indeed, the MAC is correct. So for both for proving and for verifying the authenticity, you need the secret key in a MAC. Okay. For the other ones, either you don't need the key at all, like in hash functions, or you only need the key to generate signatures, like in signatures. To generate the tag, like in signatures. Okay, next question. Which of these are security properties of a hash function? Is it unforgeability, or collision resistance, or robustness, or key recovery resistance? Yes, indeed, it's collision resistance. So the other two ones that would be correct, but that are not listed here, are pre-image and second pre-image resistance. For those who clicked unforgeability, this is the security property of a MAC, not of a hash function. Okay, and I think we got one more. How should you protect your users' passwords if you're running a server, for example? Using MD5 or AES ECB or SHA-3 or PBKDF2. That's one for the people who are really good with acronyms, which is a useful skill to have in cryptography. But admittedly a bit of a tough question. Indeed, apparently it is too tough. So that was maybe a bit misleading. What I've listed here is, on the one hand, I've listed an encryption scheme we will meet today. That's wrong, almost nobody clicked it, great. Then we have here two normal cryptographic hash functions, MD5 and SHA-3. And you're right that SHA-3 is a lot more secure than MD5, namely MD5 is not secure at all, and SHA-3 very much so. However, it's not well suited as a password hashing function. Why? Because it's too fast. So that brute forcing bad passwords is just too fast. For this reason, we have a separate design category for slow functions, namely password hashing functions. And PBKDF2, which is short for password-based key derivation function, number 2, is one of these. So that's an actual secure choice. So SHA-3 is cryptographically secure, but too fast for password protection. Okay, let's have a look at the leaderboard. Okay, there's a bit a bigger drop in points than last week, but congratulations to Max and all of the follow-up people, and a very nice number of points you got there. Okay, I guess that's it with the questions, and we can now return back to the slides. So let's see at the actual content that we've planned for today. As announced, we want to talk about confidentiality. So I'll first give a short definition of what that means and where we need that. And then we'll talk about these different layers that I promised. So actually we're going to start here from bottom up. So we're first going to talk about the lowest layer, the so-called symmetric primitives. And we will look at the most famous example of a symmetric primitive. And that is the block cipher AES. And after that, we're probably going to have a break. That's at least the plan, timing-wise. And afterwards, we're going to look at two different higher-level constructions, which are the actual functions that we want to call when we encrypt something. Pure encryption and authenticated encryption. Okay, so let's see what confidentiality is all about. So here's a definition. Confidentiality is about preventing unauthorized entities from learning information, such as messages or data, that authorized parties are communicating or processing. So let's rephrase what that means. We again have something like Bob and Alice who are talking to each other. That's totally fine. They want to share the data with each other, but they don't want anyone else to know about it. So these are the unauthorized entities, or the EVEs that are around. There are some slightly related concepts which are, however, different. So I want to make this disambiguation here at the moment. And two of those are anonymity and privacy. So what are those about? I think you can guess what the difference to anonymity is. Anonymity is always about keeping the identity of someone a secret, not any particular data that they are talking about. So anonymity is actually about the fact you have some data, it's public, it's visible, but you want to hide who generated this data. And the privacy case, this is a bit harder to see the difference. But what privacy is about is that one user wants to have control over which of their data they share at all. So it's not like you're generally sharing the data with someone and you don't want anybody else to see. But it's more about you having control over your own data and deciding which parts of it to share with the world or with a particular entity. There's often an overlap between these two. So in particular, you usually need mechanisms to protect confidentiality in order to also protect privacy. So they are closely linked, but what the cryptographic schemes protect, strictly speaking, is this property here. You're going to talk about privacy mechanisms a bit later in the course in the applications part. Okay, so let's have a look at what we do to achieve this confidentiality and which different types of schemes there are. So again, I have this sort of overview slide here where I show what confidentiality means with respect to different key configurations. Because a key is again going to be involved, because encryption schemes are all about translating a message to a ciphertext. And this translation will always depend on some key. You're getting really heavy. And additionally, they may require some additional inputs, and they might also additionally protect the authenticity with a tag. But the main thing is we have a message, we translate it to a ciphertext, and to do this, as well as to translate it back, we need a key. And in the simplest case, this key is the same for both participants. So this is a so-called encryption scheme then. We have a symmetric key where Alice and Bob share the same key. Both of them can encrypt any data with it, and both of them can decrypt any data with it. So that's the equivalent key setup that we had for a Mac. And speaking about Macs, we can actually combine the features of a Mac and an encryption scheme to get a scheme that protects both confidentiality and authenticity. And this is called authenticated encryption. And that's actually what you should use instead of plain encryption. And finally, there's a third one. You may already guess that this is going to be an asymmetric scheme. And that's the so-called key encapsulation scheme. Or sometimes also asymmetric encryption. So what's this about? It also protects only confidentiality, but here everybody is able to encrypt data, but only one person is able to decrypt. So it's not two secret mongers and Alice and Bob, but it's just Alice. Alice has a key and everybody can send Alice something using some public information about Alice. But only Alice can read it, even if all the encryption, all the data needed for encryption is publicly visible. This is what we're going to discuss next week, but the first two are this week's topic. So let's have a look at a few practical cases where you might have been in touch with encryption already, most likely, and where you might already have seen some hints at the cryptography underneath. Now there's one big difference to authentication. In the authentication lecture, we had a number of examples where you actually saw the output of the crypto scheme. You actually saw the hashes, you actually saw the max you had to type into your mobile TAN. Encryption is usually so well hidden in the scheme, or so transparent as we call it, that you don't notice much of it at all, except if you were to use, for example, a network sniffer or something. Or a direct readout of your hard drive, for example. But in the user interface, you only usually get the name of the crypto system. And one of the places where you probably have seen it before is if you click the green lock in your browser and you click at the security information. So there you can see some information about the encryption scheme. And specifically in this case, you can read that the data is protected using a very long string containing very many three-letter acronyms, which are obscenely popular in cryptography. So it's protected with TLS, AES 128, GCM, SHA 256, and an extra key size is given. So what does this mean, or what are we reading about? Why does it list so many crypto schemes here? Well, the reason is that they talk about different layers and security goals. The first one, TLS, is the name of the protocol, but everything that comes after tells us about the symmetric crypto scheme or crypto system that's used to protect the confidentiality. AES is the lowest level primitive, 128 is its bit size, GCM is its so-called mode of operation, so that tells us how to use the block cipher. And additionally, it's combined with another symmetric scheme, namely the hash for protecting the integrity, and in particular, normally as an ingredient for signature scheme or as a helper function. So the part about AES GCM, that's the part we're going to talk about today. You can also find this kind of information elsewhere. For example, if you're using Linux and you have your disk encrypted with the LUKS encryption system, which is the default in most parts, there you can also find some information about the schemes that are used. So in this example, we see that the data segments are encrypted using AES again, but in a different mode of operation called XTS. And then there's the plain part, which doesn't concern us much here. That's giving some additional specification of how the keys are treated, which we don't care about. But the AES XTS is again information about the encryption scheme. And it's the same thing on the bottom. On the bottom, actually, we see another ingredient that we've already met, namely a password-based key derivation function. Because one of the ways that cryptographic keys are also often generated is by hashing a password and generating a key from it, usually from the password plus a salt. This is necessary whenever we require a human to enter their credentials to unlock something. Okay, so why did we have this many three-letter acronyms? I already hinted at it, but I've also illustrated it in a picture. Namely, if we look at this log symbol, we have again several layers in it. I've talked about them already. Here's an illustration. So the topmost layer that we always have is protocols. And in the previous examples, this protocol is TLS. So this defines the general rules how the individuals are supposed to talk to each other, which messages they should exchange, how they should handle their keys, which other schemes to use. And schemes is the keyword because schemes is the name for the building blocks that protocols use. So schemes are cryptographic algorithms which achieve a particular security goal that makes intuitive sense. For example, an encryption scheme is a scheme. It satisfies the need for confidentiality. A hash function is also a scheme. It protects the integrity under certain constraints that we now know. So these schemes are built to work with data of arbitrary size usually, so they're very generic. But in order to achieve this, they always need a core nucleus that defines the security. So the atomic building block that makes the thing secure. And this atomic building block is the so-called primitive. For example, in the previous case is the AES block cipher. So this is a building block of fixed input size, like the compression functions we've met before, and it already has a security level tied to it. So it's secure, but it's by itself not very useful. It's not general enough to be used by a protocol. We need this layer of schemes in between. And how schemes usually use the primitives is either, for example, calling them again and again for each block of data to translate the block, or applying them to the blocks to accumulate some sort of information. This is what we've already seen with hash functions. So let's have a look at how to build such a core building block. And this will also be a good time to have a look at the questions. I'm just briefly, I just go a few slides back, then we should have room for the questions. Let's see. So the question refers to asymmetric schemes, and it asks, what is the use case of asymmetric schemes? Well, they are also used in protocols, and in particular, we usually use them in the beginning of a protocol, because we saw that for the symmetric schemes, we already need to have exchanged some information in order to be able to talk. We already need to have this key set up. And the asymmetric schemes usually come into play when we don't have that yet. It's getting really bright. I'm beginning to look like a ghost, but that's okay. Maybe I can fix it in the break. So yeah, the use case of asymmetric schemes is always to kickstart the conversation, to get the protocol started. This is usually called a handshake in the beginning. And once we've used the asymmetric schemes to set up this handshake, we can afterwards use the schemes we've heard so far to talk. Okay, back to the presentation and back to symmetric primitives, sorry. So to the secure building blocks that we want to use. Not much better without light. Okay, let me just fix this here. Sorry for a short period of noise, but I need to get the sun out of the room. So let's have a short recap of one primitive we've already heard about, namely a compression function. Now this is just a normal poll, no quiz, so no need to hurry. But have a look at these pictures, some of which you've already seen in the previous slide. And the question is, which one? Which one of these shows a compression function? Okay, there's quite a bit of disagreement. I'm not sure if everybody's answering the same question. Okay, but it looks like a winner is emerging, and indeed this winner is the correct answer. So let's have a look at these pictures. This is indeed a compression function. You can see that it has a larger input and it compresses it to a smaller output. And we also indicate it with this trapezoid shape here in the picture. Some of the other ones also have a larger input than output, but they are not actually compression functions. And one of them is this one here. This is a block cipher. You see that it also takes a large, so two inputs and produces just one output. However, you notice that the shape is different, and this is indicated to this is to indicate that we have a sort of one-to-one translation scheme here. So we can go from X to Y, but we can also go back from Y to X, if only we know the key. So for this reason, we don't call it a compression function. This here is similar. It also is like a block cipher, but it just has one more additional input, the so-called tweak. And this one here is a so-called permutation, where the input and the output are of the same size. So there is not even an additional key input. Okay, so that's for the primitive we already know. Now let's head on to a new one that is actually much more well-known generally. And that's the so-called block cipher. So block cipher is exactly what we saw in the previous picture on the rightmost side. And it has, as I already mentioned, two inputs. So one is the key of a particular size, and the other one is a message block, which also has a fixed size. And the key defines a bijective function, or permutation we also call it, which simply means a function you can compute forward and backward to translate a message block to a ciphertext block or back. And the backwards direction is also denoted by D for decryption. E is for encryption. And if you're wondering what the title is about with these spaces, in mathematics we usually call the set of all possible values in a place a space. So in particular, we have one k-bit key if we actually use it, but the set of all possible keys, those are 2 to the k many, this is called the key space. And similarly, the set of all possible plaintext blocks, since it's n bits, there are 2 to the n possible plaintext blocks, this is called the plaintext space. Sorry, this one here, of course, we need to look at encryption. This one is, of course, called the ciphertext space. So we also like to say that a block cipher defines a family of permutations. So a family of functions. What do we mean by that? We mean that each value of the key actually picks one specific such bijective function, or defines it, which we can use to go back and forth. But every other key also defines a different one. And the set of all functions defined by all of the keys is called the family, the block cipher family, or the family of permutations. And because we very often focus on this view that we have just one fixed key and we're just looking at this one bijective function, we also often draw the picture like in the following, like this. And there's one more important thing. In order to be able to visually differentiate between these two, so to make clear which of them is the key that only influences how the function works and which of them is the actual input to the function, we usually mark the key input with this triangle here. Because very often we use this in a permuted way, so we turn it this way or that, and to always be sure which one is the key, we use this triangle symbol here. Okay, and here we can either keep it or not keep it, to clarify that we have a function, e, and this is parameterized by the key k to map messages to plaintext blocks. So that's just a different notation for the same thing. Now, what do we mean by security of these schemes? We mean two things actually. The first one of them can also be called pseudo-randomness. Sounds complicated, but what it actually means is it should be impossible for an attacker to learn anything about the message just from seeing the ciphertext. So that's actually very intuitive. This is exactly what we want when we want to protect confidentiality, right? We don't want to be able to learn anything about the confidential stuff from the public stuff, but actually also vice versa. That's why it's called pseudo-randomness. So an attacker also shouldn't be able to learn anything about the ciphertext or what the ciphertext would look like just by seeing the plain text. So they should look like they were random strings. That's for an attacker who doesn't know the key. And that's the main confidentiality property. But there is an additional property that we care about that's actually closely related, and that's key recovery security. What we mean by that is that even if an attacker has access to very many such corresponding plaintext and ciphertext blocks, for example, if they know that a server has encrypted exactly these 50 websites and they even know the content of the websites and they see the ciphertext, they still, so they being the attacker, should still not be able to learn anything about the secret key used inside the system. So about the key input of this permutation. The mathematical way of phrasing this would be, even if they're allowed to query this permutation very often, which means they give it ciphertext blocks and get plaintext blocks, or the other way around, even if they can do this very often, they still cannot derive the key from them. Why is that important, even if they've already seen so much information? Well, learning the key would allow them to also encrypt and decrypt any future messages. And that's what we want to avoid. So this is why we need key recovery security. I see there's a question. Let's have a look at that. That's actually a question back to one of the quiz questions earlier. So a tweak, as I said, well, I'll hide the question and explain it in the picture. Let's show the slides again. I've lost focus, of course. So here. So we saw that, or I just explained that the key selects the permutation that maps the ciphertext and plaintext blocks to each other. The tweak is an additional input that essentially does the same thing. It also influences the permutation. The difference to the key is that a tweak would be public. And what's the purpose of a key, of a tweak? The purpose is to represent the context in which the message is sent. For example, it could be the position of the message block in a longer message, like the index of the message block. That's one possible value for the tweak. There are also other possible values. You will later see that in order to use these block ciphers for encryption, we actually have to do some not so intuitive things, or we need to use them in a rather complicated way. And one of the reasons why we do need to do this complicated stuff is because we don't have a tweak. If we would build a function in the first place which had a tweak, we would save some of our inconveniences here. So a tweakable block cipher is a relatively recent research object. So there have been some designs now, and it has turned out that they are really useful. But the standards are still all block ciphers, which are also fine because we have analyzed well how the complicated constructions that we need to do with them work. Okay, so this was all the sort of outside view of the scheme. The interface, so to say. So we focused on the size, on what the attacker should be able to do, but what we haven't answered yet at all is how to build this thing. And that's what we want to get to now, and then we can have a break. So what's the anatomy of a block cipher? How do we build this configurable permutation? So what we need to make sure is we need to fill this thing here with an algorithm that is bijective, so we can compute forwards and backwards, but it should be influenced by the key in a very complicated way, because of course nobody who doesn't have the key should be able to compute forward and backward. And we need to achieve this somehow. And all of this should be super complicated, complex, so that it's unbreakable. So how do we do this, and how do we build such a complicated function while still making it easy and efficient to implement? That's the big challenge. And there are two fundamental ideas that make this possible. So the first fundamental idea is that we have so-called round functions. What is a round function? A round function is a very simple function that is not secure by itself, but we're just going to repeat it very often. So the idea is that we can have a function here which is very easy to implement as a circuit or in software. And in order to achieve some sort of security, even though this individual function is not secure, is by repeating it very often. And this maybe sounds a bit silly, but this actually helps. So something simple iterated many times becomes something complicated. And of course, we now also need to get the key on board. And the way we do this is by having a so-called key schedule, which takes the master key, so that's the master key, and derives some individual round keys from that. So a round key is simply a secret value that is computed from the key, and that is used in one round. And typically we don't have exactly the same key in each round, because that would be a bit of an issue. So usually there's, for example, something like a linear function, or maybe also a more complicated nonlinear function that always updates this round key in each round to get all the individual keys. Okay, so now we still need to find a simple circuit that becomes secure when we iterate it, and that depends on the key in some way. So this is still something we haven't answered. And actually, cryptographers' answer to the question how the key should come into play here is typically incredibly simple. We simply XOR the key in between the rounds. So in practice, almost all widely used block ciphers follow this construction, which is called the key alternating instructions. And this key alternating construction always consists of a publicly specified round function. Then we XOR the current round key, then we do the round function again, XOR the next round key, and so on. And even though the picture doesn't show it, there's usually also a key addition after the last round and before the first round. So that's a bit of a flaw in the picture. And the reason why I want to do this simple thing with the key instead of something more complicated, well, this is actually, there are several reasons for that. One reason is that we want to avoid having any key-dependent circuitry, like key-dependent lookup tables or so in there. First, because this would be complicated to implement. It does contradict a bit Kerckhoffs's principle, and it also could be, that was not originally the reasoning, but it could be a trigger for something like side channel attacks or so, that try to look at the key-dependent circuitry and learn something about the key from it. So for this reason, we choose a very, very simple operation, namely taking the intermediate result and XORing the key, no matter what the key value is. There's also another practical reason from the perspective of a cryptanalyst, and that's that this sort of construction is reasonably well analyzable from a statistical point of view, because the key doesn't introduce any sort of bias or so. So if any bit had a 50% probability of being 1 or 0 before, and we XOR the key, which is unknown, so we can also treat it as a 50-50, the output is also 50-50. If we would use a different operation, like an AND, for example, we would have a number of issues. Among them that we would introduce a key-dependent bias, because if the key would be 0, then the output bit would always be 0. And it would also be a non-invertible function. Because of course we said, we not only want to get from the plain text block to the ciphertext block, but also backwards. In the key alternating construction, this means we need to define a round function which we can compute backwards, and we need to undo this key operation. The good thing is, undoing an XOR is very easy. You simply XOR the same value again. So the backwards direction looks just like the forward direction, except that we go from bottom up, also within the rounds. Okay, so that's the key alternating construction. Now let's have a look at one design which implements that. And as there are questions, let's look at the questions first. I again need to hide the slides for that. Let's have a look what we have here. So the first one is a question about key recovery security. And it says, can the attacker look at the pairs M or C, or can he only see many Cs? Because the first is not possible, I think. Well, fortunately, it is actually possible. some reason the question is not showing up, but I hope you could follow from my talking. And this is the crucial thing about block cipher security. So that's the key recovery security part of it. Even if we look at many pairs M and C, and actually even if we are so powerful that we can trigger the encryption algorithm to encrypt our favorite values of M and we get to see the C's, even then it's supposed to be secure. And that's the main job actually of this construction that we've seen on the previous slides. And you can maybe imagine it if I show the slide quickly. If you know this value here and this value here, you have many rounds in between, and in all of them, something that depends on the key is XORed. And if you don't know the key, knowing the two endpoints doesn't help you much, because you can't learn any of the intermediate values and also not the key. If there would only be one XOR, for example, so imagine for a moment that these two XORs are gone and we just have this one XOR here. Then you are right, then an attacker could learn the key, because they could compute from the message forwards up to here and from the ciphertext backwards up to here, and then there would be this one key in between, and they could look at it by XORing the two values. So that would be a bad design. But by having many rounds, and by many I mean anything between, let's say, 10 in some designs and 100 in some other designs, you avoid this problem. So you make sure that there are too many values in the middle that an attacker cannot get to from only seeing the endpoints. Okay, let's hide again and let's look at the next question. Why do we usually XOR the key? Why not or AND? That's a very good question. I just think I answered it sometime after you posted the question. I just repeat it again. One of the reasons that we don't use or AND is because these are non-invertible functions. If you take a value and you AND something to it, you can't get the original value back in some cases, because, for example, if the key bit would be 0 at some point, then no matter whether the intermediate, or let's say the plaintext block would be 0 or 1, the AND with the 0 would delete this information. And from seeing the output, which is definitely going to be 0, we cannot go back to learning the whether the original message block was 0 or 1. So we wouldn't be able to decrypt. And the same thing with an OR. Now, this doesn't mean that ANDs and ORs cannot appear in a cipher at all. Actually, they have to, because we need some nonlinearity. But they are not a suitable operation to use with the key. If we use them, we need to be really careful to build something that we can still decrypt. And with the key, this wouldn't be possible. And other reasons are that it introduces biases, it's more difficult to evaluate statistically, and so on. But really, decryption is the main thing. A very off-topic question: how heavy is Hexe? Well, not very heavy. She's actually just average weight. But still carrying her around for a while is inconvenient. Okay, so another question. So you could also use EK for decrypting and DK for encrypting? Yeah, totally. The two are really, for the most part, completely interchangeable. However, we need to agree on one direction, so we usually do it the way it's specified, but doing it the other way around would in most cases be no issue. There are some exceptions to this. So in some designs, the designers made sure that the encryption direction is really, really efficient at the cost that the decryption is a bit more complicated. This has a good reason, because in many applications we actually need only the encryption direction and not the decryption direction. So in that case, swapping the two would be a bit inefficient, because we were also doing the slightly more expensive backwards direction instead of forwards direction. But generally, from a functional point of view, from a security point of view, absolutely correct. Are the round keys always computed the same way for all rounds? First, to clarify, I think that's not the part of your question, but to clarify, we usually don't use exactly the same round key in each round. So here you really have a function that maps one round key to the next round key. Now, to make it easy to implement, we usually use the same update function in each step. So that's actually similar to the round function. The key schedule is often similar to the round function, and we use the same function in each step to make it as efficient to implement as possible. So we only need to implement the update function once and can reuse it all over again. However, there is one thing that is actually very often different. We will also see that later when we look at the AES design. And that is that designers very often specify a round constant. And this could be a simple counter, like it could be 1 in the first round and 2 in the second round and 3 in the third round and so on. And this is usually not updated, or this is not always updated with the same function. Let's put it like that. So some designs use something like the first round XORs the first 128 bits of the number pi, and the next one the next 128 bits of pi, and so on. So that would be an example where you don't have the exact same update function. But some designs also, to make it easy to implement, do use the same thing. So they could use, for example, a round constant update that is simply a +1, and that would be this counter style thing I mentioned before. Okay, let's look at the next one. What exactly is the round key in the second idea of the anatomy of a block cipher? So let's show the slide again. So you're probably asking what exactly this round key is here. So it's simply a value that looks like a key that is derived from the main key, but it looks a bit different in each round. So, for example, you could imagine something like in the first round you take the original key, and for the second round, for example, you could multiply it by 2 and take 2 times the key. And for the next round, you could multiply it by 2 again, so you would have 4 times the key, and so on. So you have a sort of update function to not use exactly the same bit string in each round, but it's still more or less a simple transformation of the original key. So usually it's also in a way that if you know one of the round keys, you can directly compute back to the original key. It could also be something like you take the key in each round, but you permute the bits a bit. So you put the first bit there and the second bit there and something like that. So it's just a simple function to have not exactly the same key in each round, because there are some cryptanalytic methods which could, under certain circumstances, do something bad here. Okay, let's look. Let's hide the slides again. So the last question that we have here is, oh no, it's not the last one, there are new ones. Okay, so why using round constants? It's kind of like nonce reuse if we know it has no value, or does it? Well, there is still some value to it. And one of the reasons is the so-called slide attack. This is an attack which is usually not applicable, but it's still a theoretical threat. And this could exploit if, for example, round 1 to 10 of the cipher would look exactly the same as round 2 to 10 plus the first round afterwards. So if you could sort of, it's hard to illustrate. If you have the situation that these are the 10 rounds of the cipher, and they would have exactly the same operation as going from the second round to the last round and then appending the first round, and so on, then you could create a sort of a situation where you have multiple targets that you can attack. This is a very vague explanation because the attack is a bit more complicated, but there are some cryptanalytic reasons to do that. But what value exactly we use for the round constants is usually very irrelevant, hopefully, otherwise the cipher has a problem. So that's why people very often use a very simple thing like a counter or so. Yeah. The main thing is to make sure that each round doesn't treat exactly the same input value in exactly the same way. But you're right, you're totally right, it's not immediately obvious why this helps anything at all. So why is it not enough to just XOR the round key 100 times? Okay, so if we assume, so let's put it like that. That's actually, so it first sounds a bit silly, but it's actually a good question. Let's first consider the case that I mentioned so far, that the round key is a very simple function of the key. A very simple function could, for example, be a linear function of the key, like I mentioned, permuting around the bits or maybe XORing some bits to each other. If we would do that, then we would actually only XOR a linear function of the key to the input value. And since linear functions are really easy, they can also very easily be undone. Because if you imagine the setup, I have the message, I XOR many times many linear functions of the key, and then I have the ciphertext. If I now have a known plaintext attack scenario where I know the plaintext and ciphertext, can XOR them to get back this XOR of all of the keys. And if this was only a simple function of the key, then I would be able to compute back from knowing the XOR of these functions to the original key, hypothetically. On the other hand, if I have a really complicated function for the round keys, then your concept actually goes in the direction of a different way of building ciphers, namely so-called stream ciphers. What does a stream cipher do? It doesn't exactly XOR a round key 100 times, but what it does do is it takes the input key and it computes a complicated function of the input key and XORs that to the message. And then it computes another complex function of the key and XORs that to the next part of the message, and so on. So a stream cipher does something like that, just XORing a function of the key to the message. And we'll actually later in the lecture see a different construction where we also just XOR a function of the key to the message. But there is one very important issue, and that is that if we do this, and if we look at two encrypted messages, then the process between the two would be extremely similar, because we would XOR the same value computed from the key to both messages. And that would be an issue, because if we then know one plaintext, one ciphertext, and one other ciphertext, we can compute back to the third plaintext. That was probably a bit hard to follow, but it's a topic that we'll get to later in the lecture anyways, so I'll leave it at that here for the moment. Okay, let's look at the last one. Could you use a password-based key derivation function on the key for each round? You could, but it's like throwing cannons at sparrows, so it's totally overdoing it. Usually the round key functions are really simple, because we want the whole thing to be efficient. And yeah, so it's not necessary to do it. It would be, you could do it, but the resulting cipher would be really slow, because as I said, a password-based key derivation function is designed to be slow. Okay, thanks a lot for those interesting questions, and let's show the slides again. By the way, I see some indication that my mic might be a bit too loud. In case you also think my mic is set up wrongly or too loud or so, could you maybe indicate it by pressing the question mark a few times so I know? If you don't press it, I assume it's acceptable. Okay, so now after all of these talking about the general concepts, let's have a look at an actual design that looks like that. So this design that I want to talk about, and that Hex apparently also wants to talk about, is the AES block cipher, which was found as part of a public competition. So what does AES stand for? It's one of these often mentioned three-letter acronyms that we have very often in cryptography, and it stands for Advanced Encryption Standard. Why advanced and not just encryption standard? Well, actually it's a follow-up to a previous design which was called DES, Data Encryption Standard. And they wanted a new one because the old one was pretty old, from the 70s, and had reached the end of its lifetime in the 90s. So they wanted something new. And while this old data encryption standard, which was one of the first publicly available crypto systems at all, so this old DES was actually sort of designed behind closed doors, so by IBM, but with a lot of input from the NSA and so on. And this didn't exactly help with the trust that was put in the crypto system. So many people sort of suspected that the NSA tweaked something or knew something about the DES that they didn't tell. And to get rid of this sort of problem, the organization body, the most influential one being the US standards body called NIST, National Institute of Standards and Technology, they decided that they want to try a new process. And they want to try a process which really increases the public trust in the design. And for this, they ran a competition. So they announced this competition in 1997, and they asked cryptographers all over the world to hand in their candidate designs for the new standard. And at the time, they received 15 submissions with contributions from a total of 50 cryptographers. And then these candidate submissions were evaluated for years. So the whole process took between 1997 and 2000. And they were evaluated for all kinds of things. So of course, most importantly, security. Do the designers convince the readers or the cryptographic research community that this is a sound design? So one that doesn't have any intentional weaknesses and one that doesn't have any unintentional weaknesses. Additionally, they were evaluated for how useful they are. So for example, can they be efficiently implemented on several different platforms, in hardware or in software, and so on. So a number of criteria. And the final winner of this competition, so all of these submissions had their own names when they were submitted, and the AES, for example, was called Rheindal after the first letters of the two designers, Johann Dahmen and Vincent Hyman. And this one was decided as a winner. So such competitions always go in multiple rounds, and each round some of the candidates are removed. So it's like semi-finals and finals and so on. And the final winner, as I said, was this one here. And this was really, really influential for several reasons. So first, it has more or less completely replaced the DES with good reasons, and is now used really everywhere for secure encryption. And this also makes sense, so it's more than 20 years old already, but it has been really well designed, so there's absolutely nothing to worry about in terms of its security. It has contributed a lot to the public trust in cryptography, because this was a very transparent process, and NIST made relatively clear why they made certain decisions, why they decided for a particular design. And the designers are also unsuspicious in the sense that they are academic researchers. They are not part of some secret service or some other entity that some people would trust and some others not. But just academic researchers. And additionally, the competition also gave a really big boost to the science and symmetric cryptography in general, because the AES had a very elegant and new design strategy that has very strongly influenced how other ciphers today look like. And this competition model also really has stuck with NIST. So they've now, in the meantime, had several more competitions, including for the hash function SHA-3. And there are currently 2 competitions ongoing, one for post-quantum secure cryptography and one for lightweight cryptography. And these are now attracting actually many more submissions than this first round. So we are usually now more in the 50s or 60s or something like that of submissions. And they also take longer for this reason nowadays. So more like 4 years or something like that. Or in some cases even longer. Okay, so that's the genesis process of AES. Now, how does it work? How do the round functions look like, and how is the data handled by it? So we said it's a fixed size object. So in particular, it takes a block input size of exactly 128 bits. So that's the N that we heard about before. And it actually supports 3 different key sizes. So each key size defines a separate block cipher actually. So you can choose to either use AES 128 with a 128-bit key, which is usually the default almost everywhere, But if you like to be extra sure, you can also use one of the larger 2 bit sizes, which is AES 192 or AES 256. For the most part of the description, I'm going to focus on this one because the other two are really very similar. So what does the cipher do with these 128 bits? It stores them as a matrix of bytes. So the mathematical representation of the 128 input bits is that it's chopped into 16 bytes. So 16 times 8 is 128. And these bytes are arranged in a 2-dimensional way in this sort of matrix. And the same thing is done to the key as well. So for the AES 128, we have the 4x4 matrix, and for the larger keys, we have 4x6 or 4x8 matrices. And all of the operations are now defined with respect to this matrix representation. And the individual cells are numbered as state byte 00, 10, and so on. Okay, so that's how the data is represented. Now, what does the round function do with it? Let's have a look at the first operation, because actually the round function consists of multiple operations. No worries, the slides are very empty here. If you look at the handout version of the slide, you find the text description of what I'm saying here. But I prefer to keep the space free to be able to walk around. Okay, so each round consists of several steps, and each of these steps has its own role. Let's look at the first step, which is called sub-bytes. So sub is short for substitute. And bytes are, of course, all these entries in the matrix. So what does this step do? It defines a lookup table, which is called S, which maps any 8-bit value to a corresponding 8-bit output value. So for example, the byte 00 would be mapped to the byte 63 in hexadecimal. And for all of the other values of a byte, it also defines the corresponding output value. And it's simply a complex lookup table where the rule how to translate each byte doesn't have an obvious rule. Of course, it does have a rule, but no obvious rule. And this lookup table is applied to each of the 16 bytes. So for each of the 16 bytes, let's pick this one here, we look up the table, the value in the table. So if the first row, for example, if this would be a 00, we check what does 00 map to. Okay, it maps to 63. Great. We write 63 in the same place. So what's the role of this lookup table? It's supposed to contribute to what we call confusion. Now this sounds informal, but it's actually a relatively formally defined term. And it means we want to create a complex relationship or dependency of the output on the input values. So you can imagine right before this step here, if it's the first round, we had the plain text block in the beginning, and because we were using a key alternating scheme, we already XORed the key on top. So in the first round, the input to this first operation here is the XOR of the message and the key. And we now put it into this lookup table, which is defined according to a well thought out mathematical rule, which has to do with finite fields. We create this complex dependency because this lookup table has some very nice properties. For example, one of the properties is if we look at two inputs which are similar but which have a specific difference between the two, so we know the XOR between the two, then we cannot, for example, predict the difference of the corresponding two outputs. And some other such rules which just make it difficult to approximate. So for example, it should also hold that any linear function of the input and any linear function of the output don't correlate with each other. So that's just a complicated way of saying there should be no discernible pattern in this function defined by the lookup table. So that any bit of information I know about the input shouldn't be easy to translate into any knowledge of the output. That's the purpose. And in particular, it's a nonlinear function if I would implement it as a circuit instead of a lookup table. But usually I implement it as a lookup table. So that's the first operation. It only works on a cell-by-cell level. So far there is no dependency between the cells. The next operation also doesn't really induce any dependency. It simply shifts each matrix into another, each byte into another position. So the first row actually stays the same. The next row is shifted by one position to the left. So the top rightmost value in the second row now ends up in the second position from the right. And the third row is shifted by 2 positions and the third row by 3 positions. So what you can see is that the values who used to share a column are now in different columns. It's not yet obvious why this has any use at all, but we will get to that in a moment. And this reason why this makes sense is the next function, which is called mix columns. So this is the first function that actually creates a dependency between the individual bytes. So it makes sure that they are mixed together. And this mixing is done as follows. We take the entire column, so this is a 4-byte value, and we interpret it as a bit vector or byte vector. And then we multiply it with a matrix. So the matrix is here written as a matrix of bytes, and you must imagine that each value here is actually a full byte. So this is actually not 2 but 0, 2, and this is 0, 3, and this is 0, 1, and 0, 1. So this is a matrix of 4 by 4 bytes, and it's multiplied to this vector. This multiplication is actually not exactly the kind of matrix multiplication that you know, because it doesn't interpret the values as integers. Instead, it interprets them as another mathematical object, which is called a finite field, which we don't care about in detail. But you should just be aware that if you see an implementation, you're not going to see an actual multiplication by 2 or by 3, but something slightly different because it's in a different mathematical structure. But essentially, it's still a matrix multiplication, and the resulting output vector is written in the same position. So each column is overwritten with the column multiplied by this matrix. And the purpose is now to make all of the bytes in the output depend on each byte at the input. And actually, the function is very carefully designed to actually do this, because it has some guarantees. So for example, it guarantees that if only one of the bytes changes here, actually all of the output bytes are going to change. So this is what we call diffusion. And it's designed for strong diffusion. And now we also see why the previous step makes sense. Because now we've mixed the stuff within one column, and in the next round, where the same round function is repeated again, this column is going to be shifted to 4 different columns, and then going to be mixed again. So this way we get a mixing over the entire state. That's essentially the idea. And then we have one fourth step, which we already know from the key alternating scheme, namely we simply take the current intermediate result, XOR the current round key to it, and get a next intermediate state. And after this step, we loop again and start again from the beginning. And we repeat this a total of 10 times in case of AES 128, and that's enough. So that's actually a relatively efficient function. So if in case you were wondering what the key schedule looks like in AES, it uses some similar operations. So it also uses some S boxes and some column-wise operation, but it's not exactly the same as the round function. But still, it's just a simple update that uses this kind of rule here. Okay, in case you couldn't exactly follow this or would like to get a better feeling of what, for example, changing one of the input bytes means for the intermediate results, then one thing you can do is you can, in the handout version, click the link on top here, which, if it's still valid, should point to an Excel implementation of this cipher, which sounds a bit weird, but actually makes sense, because this is a sheet which contains all of the intermediate results of an AES multiplication, and you can try out things like, what if I change one key byte here, what changes in the overall thing. So this could help you in better understanding what the AES actually does. Okay, so that's what the AES looks like. As I said, these 4 operations are repeated in each round, total of 10 times, and that gives us the final block cipher. Okay, so let's summarize this part and then finally have a short break. We're already running a bit late, but we've also already covered more than half of the lecture. So what's the conclusion of the primitive part? Primitives are really the foundation of security in symmetric cryptography. So they are the core building blocks that provide security. Anything smaller, so any of the building blocks, is not secure by itself. For example, a round is not secure by itself. Only the carefully selected number of iterations makes it secure. And this security can actually not be completely proven in a mathematical sense. So you cannot actually prove that it's impossible for an attacker to recover the key based on the plaintext and ciphertext blocks. But we have several decades worth of experience in analyzing these schemes. So we know a couple of techniques and tricks that vulnerable block ciphers are vulnerable to, but secure ones are not. That's why we have, you can compare it a bit to the case of P and NP complexity classes. We don't know exactly that NP is really infeasible, but we are pretty confident because we've been analyzing the problems in it for a very long time. Okay, so which primitives are there out there that you might want to have heard about? So definitely the AES, in the symmetric world, the most influential primitive. If I take as an example the current HTTPS protocol version, which is 1.3, then you can choose these two variants of AES as a primitive. You can also choose something different, namely a stream cipher called CHA-20. This is a newer design. It hasn't received as much analysis as AES and it's not standardized, but it's still quite trusted very widely. Also by an academic researcher. And finally, there's the SHA compression function, which works a bit differently than the AES, but shares the same concept. So we also have these round functions where we also have linear and nonlinear building blocks. But because hash functions always need bigger outputs to protect against collisions, we also have a bigger state size in there. And all of these primitives that I've listed here that you can choose in TLS 1.3 are expected to provide long-term security. And long-term also means there is no drastic threat from quantum computers. So these symmetric schemes only lose a bit of security in case of quantum computers, but not enough to make them actually vulnerable. Okay, so with that, I'd like to finish this part here and do a short break. Maybe not do it too long, so I would suggest something like 8 minutes or so. So I would suggest that we continue at 11:05. And yeah, in the meantime, grab a coffee or otherwise clear your head or try to process some of the things that I talked about. And afterwards, we'll also get to the questions you've asked in the meantime. Okay, have a happy break and see you again in 7 to 8 minutes. Trigger. So, bin leider noch nicht fertig. Dauert noch. Oh, Trigger bekommst du nichts zu essen. Okay, here we go again. Welcome back from the break. And I had the chance to look at some of the questions in the meantime, so let's look at them together. There are actually some quite interesting ones. So, the first one is whether, so that's relevant for the exam, whether you need to know the AES rounds by heart. Well, I would say in parts. You should know which operations there are in general and what very roughly they do. So you should know that there's a sub-bytes lookup table, a shift rows shifting around, a mix columns which mixes columns, and the key addition. You do not need to know what exactly the matrix looks like or in which direction the shift columns goes. That's really not so relevant. But knowing that there are these two different kinds of operations and that they play together, that's really essential thing that I wanted to get across, so that you should also know for the exam. So the complex lookup table plus diffusing this effect in the whole state. Then, where does the lookup table for AES come from? Is it fixed for any given implementation? Yes, it's fixed. So there's one known, one fixed table that's always used. The same in each byte, the same in each evaluation of the cipher. And it's defined, so actually in a mathematically relatively elegant way. It's also linked to these fields that I mentioned. And actually this function is a sort of inverse function in this field. I really don't have time to go into the details. If you would like to know more, you can have a look at the cryptography lecture, but it's a bit more complex to explain than I would like to do here. But it's a fixed function, and it was chosen because it is nice and elegant, and because it's secure against many of these properties that I mentioned before. Like it's not easy to find a simple approximation of the function or a pattern in the function. Then, if it's only efficiency and invertibility that is important for round functions, would XNOR also work? So I guess this refers to the way that the key is linked to the round function, and there we could also do XNOR, which is closely related to XOR. For the round function itself, we do need something more complicated than just XORing things, because we need something nonlinear, like the S-box table. Then, who defines the lookup table? Is it always the same? Yes, it's defined by the designer of the crypto system, and they have to provide very good reasons why it looks this way. And then everybody needs to use it. So the security of the cipher very crucially depends on what this lookup table looks like, so please don't exchange it for anything else. It was defined very carefully, you can be sure of that. Is the lecture Cryptography happening this semester? Yes, it is, but it's actually happening on campus because there are not as many participants as in this course, as it's a master course. So if you're interested, you can either join. It's actually always in Fridays in the afternoon. And if you don't want to join, but you're still curious, you can also find the recordings from last year in my YouTube site. And can I explain more about the mathematical field which is used in the AES? Well, not much more, except to say it's simply a way of computing with, for example, byte-sized values in a way that doesn't have any overflows or so. So, for example, if you would interpret all the bytes as integers and you would add them, you would at some point either have overflows or need to ignore the overflows, which means computing modulo 2 to the 8 essentially. And this mathematical field does something cleverer than just computing modulo 2 to the 8. Yeah, that's essentially all I want to say about it. It's just a way of doing addition and multiplication with, for example, byte-sized objects. Could also be larger, but it needs to be of a fixed size. And if you want to know more about it, you can search for the keyword finite field or Galois field. There's also a lecture unit in cryptography where I explain this in more detail. Namely, I think it's the lecture that's called elliptic curve cryptography, because there I first need to explain fields. Okay, so now that we have a primitive to use, let's have a look at how to use it. Oh, and there is one more add-on that I wanted to provide before we go there. I just remembered in the break that last time somebody asked, okay, but how do we make a compression function? How do we make sure that we can't invert the function? Because in the AES, let's quickly have a look at how inverting works there. Need to change the focus again. Yeah, so let's quickly look back at the definition. So we already saw how to undo the round key. We simply XOR the key again and would get the original value. How do we undo the mixed columns? Well, we take this column and multiply it with the inverse matrix of this matrix and get this. How do we undo the shifting? Well, it's easy, we shift in the other direction. And how do we undo the S boxes? Well, we simply use the lookup table in the reverse way. So instead of looking up the value in the top row and then taking the value in the bottom row for the output, we look up the value in the bottom row, search it there, or store the inverse table, and then look up to the top row to get this input value. So this is how to undo all of the operations in AES for decryption. But what if we don't want to have an invertible function? I just very briefly want to show you how you could take a block cipher and make something non-invertible out of it. So I made this on paper because I don't have a whiteboard at the moment, but I hope you can still see it reasonably well. Well, it's actually difficult, but like this it works. So one way to do this is you take the inputs that you want to compress, so the state input and the message block input. You put the state input as an input to the block cipher and you use the message like the key. Now, so far this would still be invertible, right? For example, you could take any value of the message block, put it in there and go backward and we would have a valid pre-image. But what you can do is you can take this message block and XOR it again at the output. And now suddenly you can't go backward anymore. So from this value here, you cannot go back because you don't know this input yet to undo the XOR. You also don't need that output to learn the S. And even if you would guess some value of S, you cannot go back either, because for that you would need to know a suitable key that maps this output here to this S. So any of these combinations doesn't work. This is called the Davis-Meyer construction. You don't need to know it, I just wanted to mention it as an easy to understand way how to make a function non-invertible. Okay, to get back from the lecture, no, I don't want the Menti yet, I want the next slide. So let's have a look at how to use this block cipher to actually encrypt stuff. Now there's actually one method which seems pretty obvious. So we have a building block that can translate an individual message block. Now if we have a longer message of many blocks, we could of course simply take each of the blocks, encrypt it, and get the corresponding ciphertext blocks. That would be a very easy approach. We use the same key for all of them because we can't have arbitrarily many keys. And this so-called mode of operation, so mode of operation means it's a recipe how to use the primitive, actually exists. It's called the electronic codebook mode, and it's very unpopular because it is extremely insecure. And to see why it is insecure, there's also a very famous illustrative picture, namely what happens if you use this mode of operation for an input message which has some sort of structure. Like, for example, this picture here. This is also just a string of bytes. If you encode it in a very trivial way, you could encrypt it. And the corresponding ciphertext block, if you would interpret it as a picture again, would look something like this. Now the big question is, why is that? And what are the two major problems of this mode of operation? This is what I want to ask you in the Menti. So there are a few options here. Let's have a look. The first one option is that the AES block size is too small. The second option here is that identical blocks are encrypted to the same ciphertext blocks. The third option here is that it's not possible to decrypt, and the fourth option here is that identical messages are encrypted to the same ciphertexts. Let's have a few opinions on what you think is a bad idea. Okay, and it seems like there's a very, very clear winner, but two people also had a contrary opinion. And the good news is, all of you who did vote something voted correctly. So I already hinted there are two major problems, and these two are the two major problems. So let's have a look back at the picture at why these two happen. So the first most popular answer here is that identical message blocks are always mapped to the same ciphertext blocks. And this is quite obviously the case. So if I take the same block cipher with the same key and put the same message in, I get the same ciphertext out. And this is also what happens a lot in this picture. So for example, all the white parts in these pictures, sorry, all the white parts are translated to the same kind of grayish color, or all the black parts are also translated to the same other color. You will notice that on the borders it's not quite so clear, and this is because of the block size of the block cipher. So for example, these blocks here are all just white, but then there is one block which has some white and some black. And this is maybe a block which doesn't appear anywhere else, so this might actually have a unique value here. But the parts that are exactly the same also look exactly the same here. And finally, also if I encrypt exactly the same penguin twice, I of course get exactly the same ciphertext. Now, why are both of those a problem? Of course, normally if I do send my pictures, I don't encode them in such a trivial way, so it wouldn't actually look like that. And why is it so harmful if such patterns are visible? But actually, in reality, there are a lot of cases where we have patterns and they are pretty obvious. So for example, if I send a website, then, for example, the first part of the website always looks the same, which is a pattern I could recognize. So I would, for example, recognize if a person goes to the same website twice. And that's actually something I don't want to be visible in the ciphertext. Maybe I can learn it in some other way, but it shouldn't be something visible in the ciphertext. Or if you think of a military context, assume that one time I send a particular command, and I send exactly the same command at a later point, then anybody who has observed the output of the first one also will know what's going to happen as a result of the second one, because they know it's exactly the same command. And even if it's not exactly the same, even if just the first part of it is the same, and for example, just a small part of it, like the time of day or so, is different, this will also be visible with this mode. So for example, the first blocks here could all be, well, we are going to, I don't know, move our troops from this place to that place at, and then a specific date. And if the date would be different, then all of these blocks would still lead to exactly the same ciphertext. And somebody who observes the communication would notice that. So that's a big issue. Both the fact that individual blocks that are repeated are visible, that's what we see in the picture, and that completely repeated messages also look the same. So we obviously need to do something about that. We need to hide this kind of patterns or repetitions. And what can we do about it? I mean, we have some completely deterministic functions here. So of course, if I put the same input in, I always get the same output. So what we clearly need to do is we need to make sure that we never put in exactly the same value. But we often want to communicate exactly the same information, so we need to get this extra spicy input from somewhere else. So we need to add some randomness to this process, some external randomizer. And this randomizer is the so-called nonce, which you will encounter a lot in your KU exercises. So this is why the definition of an encryption scheme is a bit more complicated than we would assume. Because the obvious part of an encryption system, which I denote here by a calligraphic E, is that it takes a key, which again uses this F2 notation. F2 is, by the way, also short for finite field, but with bits it looks exactly the same, as we know. So we have the key, and we have an arbitrary size message that we want to encrypt to a ciphertext of approximately the same size. But we have this extra input here, the nonce, which is supposed to randomize the whole process. If you are already listening in the previous part, you might have a sort of déjà vu here. It might sound a bit like what I said about the tweak, and that's actually true. So the nonce and the tweak are somewhat comparable. Okay, and the decryption scheme should take the same key, should take the ciphertext of arbitrary length, and should also get as an input this full randomness here that we used for the encryption, and give us back the original message. So that's the scheme we want to have from a functional perspective. And this nonce here, where nonce is short for a number only used once, this is what's supposed to make sure that an adversary can't tell if two encrypted messages are the same plain texts. Because of this randomizer, if I encrypt the same message twice, I will always use different nonces, and for this reason, the ciphertext will also look different. And now, of course, the important question is, where do I get this nonce from? Now, this depends a bit on the scheme. And if you use a crypto library, hopefully the crypto library handles it for you in a good way. And two good ways are, it can be randomly generated, or it can simply be a message counter or something like that. So you use 1 for the first message, 2 for the second message, and so on. Both of them have their advantages and disadvantages. The advantage of the counter is that it's definitely never going to repeat. We are always counting up. The downside is that this doesn't actually work for some schemes. So some schemes are so fragile that you can't use counters. On the other hand, you can use actual randomness, so unpredictable values that you generate using a random number generator. That always works, but of course this has a certain danger of colliding values. So if you generate random values, by accident they could collide. Think of the birthday paradox. So that's something that could go wrong here. For this reason, you find both variants, depending on the circumstances. So how do we use it? How do we use the scheme? So Alice, if she wants to send a message to Bob, needs to have a shared secret key with Bob. She takes the message she wants to encrypt, plus the nonce value that she generated in some way, and plugs them into the encryption algorithm. She will get a ciphertext of approximately the same size as the message. It might be a tiny bit longer for padding reasons, but otherwise the same. And now she needs to send both of these values. So both the nonce and the ciphertext need to be sent, so that Bob can plug both the nonce and the ciphertext into the decryption algorithm together with his key to get the message. So the challenge of protecting the message M and its confidentiality is shifted to protecting the key again. So again, as long as the key is secure, which means unknown to the adversary, the messages also remain confidential. Okay, let's do question time before we go to the modes, how to do this. So the first question is, why is ECB, so the weak mode we saw before, is still used, and are there different use cases for the different modes of operation? Well, actually, it's hopefully not used anywhere. Whenever ECB is used anywhere, this is a mistake of the implementer. I cannot think of a single application except for messages which are guaranteed to be only 1 block in size to use this mode. So it's never ever a good idea. But one of the big issues is that a long time ago, when the DES was standardized, NIST also standardized some modes of operation. And for this, they didn't think like what is the best mode of operation or so, but they simply standardized and gave names to all the possible modes that they could think of. And ECB was one of them. And for this reason, people still know it and it has an actual name, but it's really never a good idea to use. So it's really a big red flag. Whenever you see ECB anywhere, please make a white girth around this software project. And better even inform the implementers. So how does Bob get the same or the right key? That's the big question of symmetric cryptography in general, and we will see the answer to it next week. In short, the answer is they need to use asymmetric cryptography usually. Or they have some very convenient circumstances where they know each other in real life and can share the keys. But in 99.999% of all cases, they do it using asymmetric cryptography. One more comment maybe at this point. So far we've always treated Bob and Alice as two different people, but actually sometimes they are the same people. So for example, if you think of disk encryption, Alice and Bob are both the owner of the hard disk, but they are different in time. So the one is at the time of encryption and the other one is at the time of reading. So in that case, they both get the same key because they both know the password to the hard disk. So ECB is used in some wireless keyboards, you heard. Well, I heard that too, but I think that's a myth created in the exercises. I mean, unfortunately, as I said, there are really people who use it, but it's never a good idea. Okay, if you publicly share the nonce by sending it through an insecure channel, why is it even useful? The attacker can do the same analysis as before because he knows the nonce. Yes, he knows the nonce. However, he cannot detect whether the messages are the same because he doesn't have the key and thus cannot evaluate the encryption scheme. So they see the nonce, but it's a useless value to them. They can't do any computations with it that would tell them whether the message that was encrypted is the same as before. So it doesn't add security in the sense of the secret key that you have more key material, but it really only serves to hide patterns and repetitions because the ciphertext is going to be different. For sharing the key using Diffie-Hellman would be a possible method. Absolutely right. So this is indeed one of the asymmetric schemes that you can use to exchange keys, and I'll explain it to you next week. Why is the attacker always a he? Can you say the attacker is a she from now on? This is actually a long-standing topic in cryptography, long before it was a topic elsewhere. Classically, the attacker is actually a she because they happen to be named Eve, like the eavesdropper. So very often in crypto books you find a she. I personally just always call them they because I'm really too lazy to decide who they are and I don't care who they are. So, okay, but either way is absolutely fine. Okay, let's see. So I see there is a comment by Daniel in the chat that this is actually not a myth at all, but something that was actually observed. So I just need to wait for the questions to disappear, which they don't want to do for some reason. Let's refresh Menti. And in the meantime, let's have a look at the first mode of operation that works, unlike ECB. So that works and is actually secure. And since the questions don't want to disappear by themselves, I guess I'll have to hide them on the slides. Okay, so I'm sorry, that means I won't see the reactions anymore, but yeah, let's check at a later point whether Menti has recovered. And for now, let's have a look at one mode of operation that addresses this challenge of identical blocks always looking the same in the output. Oh, now we're not showing anything anymore. Oh, that's wrong. So here this looks better. Okay, so this mode that I want to talk about is called Cipher Block Chaining Mode, or in short, we always need a 3-letter acronym, it's called CBC. So what does this mode do? It still tries to encrypt a message of arbitrary length, and it still chops up the message into blocks of the same size, namely the size of the block cipher. And it still encrypts them with the block cipher, but it does one more thing before the message goes into the block cipher. Namely, it XORs a masking value to each of the inputs. The first masking value that we have is the nonce itself, so the randomizer that we had. So this masked message is encrypted. And for the next one, we always need to use the previous ciphertext block and XOR it to the message. So this is why it's called chaining, because we always use the previous cipher block for chaining, in the sense of chaining these blocks together. Now, the encryption of each message block thus depends on all previous ciphertext blocks. So for example, the last one here depends on C2 and C2 depends on C1, so it depends on all previous ciphertext blocks. And only if they would all be the same, the encryption of the last block would also be the same as in a second message. However, to prevent that this happens at all, we kickstart this chain with this random value. So that starting from the first message already, we have this masked value and thus no repetitions. Okay, so that's the idea. This is one of the examples of a scheme where we actually can't use a counter here, but absolutely need a random, unpredictable nonce value. There's one other thing that we need to discuss here, and that is the fact that we don't know yet exactly how we really can encrypt messages of arbitrary length. We know how we can do a message that has a length that is a multiple of the block size, but this is typically not always the case. So what we need is a sort of padding scheme like we had in the hash functions already, in order to pad the message to a slightly longer length that is a multiple of the block size. And there are a couple of schemes how to do that, but essentially you just fill up the remaining missing bytes to the next block size multiple with a value that indicates how much you filled it up. So for example, if you need to add 1 byte, you write a 1 byte 1. If you need to add 2 bytes, you add 2 bytes which are both the value 2 or something like that. There are also some other tricks, such as ciphertext stealing, but I don't want to discuss them in detail. The important thing is you always need to apply this padding scheme first in order to be sure that you really can do arbitrary length messages. Okay, so that's the cipher block chaining mode, and it goes on for several slides apparently. Let me check what's wrong here. Yeah, and there is one other mode that I also want to present that doesn't do this chaining here. Now the chaining is a nice idea because you can be sure that everything depends on the previous message blocks and thus on the context. However, it also has a disadvantage, and that is that it's not really parallelizable. So assume that you have a long message and you already get all of this message in the beginning. Ideally, you would, for example, like to use the parallelism of your CPU to do some of the encryption in parallel. You can't do this here because you always need to wait for the first ciphertext block to finish before you can start encrypting the second one, and so on. So it's naturally not parallelizable, and that's a pity. And for this reason, we also have some other modes, such as the so-called counter mode, which do not have this dependency, but still do not have the weaknesses that we saw in ECB. And the most famous such mode is the so-called counter mode. Now, here we don't have 3 words to make up the acronym, but we still want a 3-letter acronym, so we simply call it CTR, like counter. So what does this mode do? There is one very notable difference. It doesn't actually plug the message blocks as a message into the block cipher at all. Instead, it encrypts a different value, namely a counter value. That's where it takes its name from. And this counter value is supposed to be different for every block in every message. So for this reason, it has 2 counterparts actually. It has a counterpart that counts the ID of the message block to make sure that all of the blocks within a message have a different counter. And to make sure that they're also different between different messages, we include the nonce here. So we concatenate the nonce and the counter. Since the overall value still needs to be exactly the size of the input block here, we actually need a slightly shorter nonce here than in the previous mode, because both the nonce plus the message block counter need to fit into the input. So what do? We take these counters, we encrypt all of them, and now as a result here, this intermediate value, this is a value that depends on the nonce and on the key and on the block position. We also call this here a key stream, because it depends on the key and not on the message. And we can now simply take this key stream and XOR it to the message blocks, to get the ciphertext. So this is a bit similar to the question that one of you asked in the beginning, whether it wouldn't be sufficient to just XOR the key. Well, it's not sufficient to XOR the key, because then we would have the same weakness as ECB and even worse actually. And for this reason, we need to get the counter into it, and a complicated function of the counter and the key. Okay, so this is the counter mode. One of the advantages is that here the nonce can actually be a counter in itself. So this is generally a bit more robust than the mode we saw on the previous slide. And it also has this, this advantage that you can actually do some of the computation in parallel. So really use the multi-threading capabilities of your CPU, for example, or just its pipelining capability really. Okay, another advantage is that here I don't actually need to care so much about the padding. Because what if the last block is shorter? So say, for example, the last block is only 1 byte long. Well, then I simply don't take the entire keystream block here of 128 bits, but I just take the first 8 bits of it, XOR to the message, and that's it. I don't need to do any padding. This also means that the ciphertext is always exactly the same length as the plaintext. Whereas here it's usually a tiny bit longer because of the last padding block. Okay, so these are two of the most famous encryption modes, and you will see that actually the second one here, the counter, is the one that's most often used nowadays. However, the previous one also has its applications, and in particular it also gives us a nice way to construct a message authentication code. It's called CBCMAC. Okay, so do we now have everything that we need to encrypt safely in practice? Well, we do have two nice modes, but they only provide confidentiality, no authenticity. And in fact, in reality, there are very few applications which need pure unauthenticated encryption. One of the few examples where we do sometimes use encryption without authenticity is when we encrypt our file systems. And one of the reasons is that it's usually hard for an attacker to manipulate the file system. And the second is that it's actually a bit hard to fit the extra values like the tag on the hard disk. It's possible, but it's inconvenient. So for this reason, in file encryption, we often use pure authentication. Actually, none of the two modes we saw so far, but one of the most popular ones is called XTS. You saw that on one of the previous slides where I showed the looks picture. But when you do actual communication, so you're actually communicating over an insecure channel, you usually want to use authenticated encryption instead. So let's have a quick look at that, and let's also try to see whether Menti recovered in the meantime and whether there are any questions. So I see there are questions. Let's see if we can project them or not. Well, let's show the Menti, but not the slides. So the first question is, if we encrypt something with an n-sized key, is the output n-sized as well? I'm not sure what this means exactly, but so usually the message block and the key can have different sizes. In AES, they're the same. They're both 128 bits in the default case, but the key could also be, for example, 256 bits. And the ciphertext block size is always the same as the message block size. So also in the previous picture, which I can't show now, you will see that the end bits are always for the message and ciphertext blocks, or in counter mode for the block of the nonce and the counter. So I'm not exactly sure what this answers. Maybe you can try again and rephrase it to make clear what you mean. Also in the counter mode, the key stream blocks are the same size as the block cipher block size, not the key size. So, what if you know the previous ciphertext block in CBC? Well, if you know the block, you can learn a bit about the message. So if you know two consecutive ciphertext blocks, and one of the ciphertext blocks happens to be identical to one you saw in another message, then if you know that the input to these block cipher calls was the same. And if you know both of the previous ciphertext blocks, you can XOR them, and then you will learn the difference between the message blocks. So you do learn a tiny bit about the message, but only under very certain circumstances, namely if the two ciphertext blocks actually collided. And the thing is that this only happens by chance, not because of any structure in the data, you can't trigger it, but only by accident. So it depends again on the birthday paradox. So if you have a 128-bit block cipher, this will only happen with a probability of 2 to the minus 64, which is really, really negligible. And only if this happens by accident, which will practically never happen, then you can learn a tiny bit about the message, namely the difference between this message block in the one and in the other message. So you learn a lot less than in ECB, and in particular, it practically never happens because 2 to the minus 64 is too tiny to ever happen. Then, what if you know how the counter is computed in counter? Well, you actually do know how the counter is computed in counter because as an adversary, you see the nonce and you know that the second part is simply 1, 2, 3 and so on, a simple counter. So you exactly know the inputs to the block cipher calls in counter mode, but because we have a strong block cipher, we said earlier that this should be pseudo-random, so this shouldn't allow you to deduce anything about the corresponding key stream blocks, and thus you don't learn anything about the message. If you are referring to when the attacker knows how the nonce is computed, then this still isn't the problem, assuming this computation is secure, so the nonce never repeats. Of course, if you are able to somehow manipulate the nonce so that the same nonce is used multiple times, then you will get two messages that have the same key stream. And then you actually do learn again the difference between the corresponding plain texts. Okay, so this is only if it's securely implemented, and on the previous question is the answer was, well, it happens with only negligible probability. Okay, great. Then let's see if it closes now. Yes, okay, so apparently Menti has woken up again, and we can have a look in the last few minutes at the very last part of the lecture, and that is authenticated encryption. So the question for this last part is, how do we combine the two keyed schemes that satisfy different security goals that we've already seen today? So we've seen a pure encryption scheme for confidentiality, and we've briefly seen in the beginning the message authentication code for authenticity. And now the question is, how do I bring both of them together and why would I want to do that? Let's first get to the why. And let's first get the focus back on the slides. Okay. So the main reasoning why you would want to do it is that if your data is worth encrypting, so it's sensitive enough to be encrypted to protect its confidentiality, then you almost certainly don't want that anybody manipulates it. Because apparently it is sensitive, important information. So that's by itself should actually be reason enough to combine both mechanisms and satisfy both security goals, where these two goals are confidentiality as provided by encryption schemes or by encryption modes, and authenticity plus integrity as provided by message authentication codes. So MECs, as we saw in the beginning. So to recall, if you've already forgotten, this was where you plugged in the message, arbitrarily long, and you got out a short authentication tag as a result. And we want to combine the two, so ciphertext plus authentication tag. And we don't only want to do this because our data is really sensitive, but also because it actually turns out that if you just do pure encryption, you might not even achieve the highest notion of security in terms of confidentiality. So depending on what an attacker exactly can do, they might even be able to defeat the confidentiality if they're able to do certain types of queries. Okay, so let's have a look at what the interface looks like. And I have to warn you, the next slide looks a bit wild because modern authenticated encryption schemes really have many different inputs and several outputs. So it's a bit messier than pure encryption schemes. But since you already know these two, I think you should be able to find your way through this definition. So here it is. What does an authenticated encryption scheme do? Actually, we usually call them not just authenticated encryption schemes unless we are lazy. Actually, they are called authenticated encryption with associated data. And the short acronym for that is AEAD. So what does it do? It protects the confidentiality plus the authenticity of a message. And additionally, it also has this supports this associated data, and specifically it protects the authenticity of this associated data. So what does that mean in terms of the interface? We again have two functions, an authenticated encryption function and an authenticated decryption function. It's coincidental that the AEAD is the same as up here. That's coincidence. So what do they both do? They both take a key. They also both take a nonce. We already know this from pure encryption schemes. And additionally, they have two inputs of arbitrary length. One is the plain text message that is treated like in the encryption schemes, but we also have the so-called associated data. Of this, we don't want to protect the confidentiality, but only the authenticity. I'll get to why we would want to do that in a moment. So these are our four inputs, and we get two outputs, or an output of two parts. The first one is the ciphertext to protect the confidentiality of the message, and the second part, T, the tag, protects the authenticity. So here are the corresponding letters. K is the key, N is the nonce, A is the associated data, M is the message, C is the ciphertext, and T is the tag. And for the decryption function, we also need to plug in, as with encryption schemes, the nonce and the ciphertext, plus additionally the tag to verify authenticity, plus additionally we also needed to tell it the associated data, because this is not encoded as part of the ciphertext. So this is why we even have 5 inputs here. And the output is one of two things. It's either the message in case the decryption was successful, and in particular the tag was verified successfully. Then we get the message back. If there was an error with the tag, we get an error symbol, which is here denoted by this bottom symbol, but which will usually be some sort of error flag or exception or so in an implementation. Okay, so these are the two functions. How do we use them? Picture looks similar as before, we just have many more letters. So if Alice wants to send the encrypted protected message, she plugs nonce associated data and message into the authenticated encryption scheme with her key, gets the ciphertext and tag, and she sends everything except for the confidential message. You notice here all the solidly colored icons are the public information, so in particular the associated data is assumed to be public information. So this could, for example, be some sort of metadata that isn't confidential and that may even be needed during the transmission. So for example, this could be some sort of addressing or metadata information that is sent along with the message, like from whom to whom this is sent or in which context or something like that. So something that's not confidential and we send it along, but its integrity is protected by the tag as well. So if Eve is being evil and tries to manipulate the associated data, then Bob will notice this during decryption. Similarly, if she tries to do anything with the ciphertext to manipulate the message, Bob will also notice, because this is also protected by the tag. And actually Bob will even notice if she tries to mess around with the nonce or with the tag itself. All of this is going to be detected when Bob plugs all of the values he receives plus the key into the decryption scheme and gets either a message or a warning symbol. And as before, it's really, really important that this nonce never repeats. Otherwise we have same sort of problems, or maybe even worse problems than in the encryption case. There's also another important thing that you need to take into account when you implement this, namely, in case there is actually a failure during decryption. So Bob notices during decryption that the tag is wrong, then the implementation must really absolutely not release any parts of the plaintext, not even by accident. So it's not sufficient to flag the error. You also need to be sure that any parts of the message that you've already produced are not visible to the user. They are destroyed, because they could be exploited by the adversary. So finally, let's have a look at one example for a scheme which implements authenticated encryption. And you will see that it essentially takes a full message authentication code plus a full encryption scheme and simply computes both of them. Well, I'm saying simply, but it's actually not that simple, and it's actually really easy to get wrong. So if you do authenticated encryption, please be sure to use a predefined authenticated encryption mode. Do not try to plug together a MAC and an encryption scheme by yourself, because this can go really wrong. This is a bit counterintuitive, but it can go really wrong. So how do we do this? What we see here is an example of the CCM mode, where CCM is a three-letter acronym for Counter Encryption Mode. This is what we see here. Plus CBC MAC Message Authentication Code. And the M is for the MAC. So let's first look at the counter mode. This looks exactly like before, right? So we have the blocks of the message and we encrypt them all by XORing it to the key stream we get from the encrypted counters. There's one thing to note though, we do not only encrypt the message, but we actually encrypt an additional value. This is sort of like an intermediate tag, message authentication code, but to get the final tag, we actually also encrypt it in the scheme to get the actual tag that we send along with the message. And to get this intermediate tag value, what we did is we performed what is called the CBC MAC, which I haven't explained in detail before, but you will see it looks actually exactly like the CBC encryption mode, except that we drop all the intermediate ciphertext blocks and only take the last one. So more precisely, for each block of the message as well as the associated data, plus some helper values which depend on the nonce here, we always take the current block, encrypt it, XOR the next block, encrypt it again, and so on, XOR the next block, encrypt it again, and so on, until we get this intermediate value here. Okay, so that's the complete scheme. You see the MAC on top, the encryption scheme on the bottom. Yeah, and this is actually one of the modes that you can, for example, choose even in TLS 1.3 still. Yes. So in TLS 1.3, so again, that's the HTTPS protocol, you can choose either this mode we just saw or the so-called AES GCM mode, which also takes the counter encryption mode, but it uses a different MAC. So you see here, this was also again a not parallelizable thing and a relatively expensive thing. And GCM has a cheaper version for the MAC essentially, but it also uses AES for the encryption part. And there's a third choice, which again uses this other primitive I've mentioned before, CHA-20, and combines it with a MAC called Poly1305. And this is a non-AES based alternative. So it's in there because some people say, to be sure, we should have a backup solution which doesn't include the AES. And this is it. Okay, so this much for authenticated encryption schemes. You can happily use any of those. They're all great choices. All of them have their own small individual advantages or disadvantages, but they're all really good. So to conclude, we looked at symmetric schemes that protect confidentiality and or integrity so far. And symmetric schemes can achieve even both of that at the same time. We saw that the security of these schemes really relies on the primitives. So in our case, on the block cipher that is underneath. And the recipe how to use this primitive is called the mode of operation. And we also saw that there are different options for protecting confidentiality. First, there's the pure encryption, where you should be careful and notice that it doesn't provide authenticity. So usually instead you want authenticated encryption. And third, there's this asymmetric encryption or key encapsulation variant, which we're going to talk about next time. In the meantime, we can still look at some of your questions, and I also have one or two questions of my own for you. So let's first look at your question. So it says, why is it a problem to use the same key for encryption and authentication? Okay, that's an advanced question. It can be a problem under certain circumstances, and in particular, the security proofs always assume that you have two separate keys. There are some situations where using exactly the same key for the encryption and the authentication can be an issue. And one of the examples is if you combine CBC encryption and CBC MAC with the same key, then you actually lose your authenticity. I don't want to go into detail why, but there are corner cases where it's a problem. However, in most cases, it's not a real problem. So for this reason, you still usually, in most protocols, still only need one 128-bit key for both of them together. It really depends on the details of the scheme. Some modes of operation also cheat a bit and sort of do a separate key by taking the master key and simply encrypting it one more time or so to get the other key. So if any of the other people in the audience is confused by the question, that's not a big issue. So it wasn't my goal to explain today. You can just see authenticated encryption as one object, and you just plug in one key and it's going to be fine. Just don't do it on your own and don't try to combine a MAC and an encryption scheme yourself. Okay, so I still have two questions here for you, and the first of them is, let's see if it shows up. Let's close the thing again. Okay, so what I'm curious about is what's a new word or concept that you've learned today? So just to help yourself in recapitulating what you heard about and maybe trying to remember back, I see that somebody heard about CBC and tweak. Let's see what else you've got. So we have some real specialists in remembering 3-letter acronyms here. That's great. I see also some not very closely related topics, but oh well. Okay, so we have a really nice overview of some of the different schemes we heard about. Maybe you also remember some particular threats or attack vectors that we discussed, or things that can go wrong with symmetric crypto if you don't use it properly. So you also heard about some new ingredients or inputs, like the nonce or the associated data. What else do I see? Everything new, okay, that's probably to be expected, since I guess you haven't heard about it in a previous lecture. What else do we have? Yeah, the concept of primitives is a very important one, so the core building blocks that offer security. Let's see if something else is coming along. The gender of the attacker. Oh yes, some of you learned about the second cat, the mysterious second cat. Okay, it looks like it has more or less stabilized. So let's have a look at a second question that I have. Some new things appeared, so thanks for that. So how much would you say that you understood the explanations and material so far? So ranging from everything without problem to utterly incomprehensible, I have no idea what's going on. So let's have a look at that. Okay, so it appears that the majority belongs to this faction here. That's great. So understood most of it, but some parts are tricky. I totally agree, some parts are definitely tricky. For those of you in this faction here, if you have any specific tips or things that you would like to hear in more detail, or some suggestions about how the lecture could be improved for you, I'm very happy to hear about those, either as a comment in the question or on Discord or whatever. Okay, but overall, this looks like a relatively good picture, I have to say. Okay, so thanks for your inputs on this one. Let's see if there are any more questions, but I don't think so. So thanks a lot for your patience. I've really used my time up to the last minute. So I hope you have a great weekend or enjoy the exercises, which I think happen in the afternoon. And well, enjoy your lunch. Bye.